Assalamu alaikum. My name is Mubin Malik, and in this lab 7 we were assigned with a task of creating or randomly generating a truth table with at least 4 inputs and a minimum of 8 ones in its output. Now this is the truth table I have made, and A, B, C and D are its 4 inputs, and 1, 2, 3, 4, 5, 6, 7 and 8 are the 8 highs in the output. Now our main task was to make a standard SOP, or the sum of products form, from this truth table, and we have to see if that standard SOP is actually following this output, or it gives the correct output at the given input. Now this is the standard SOP form, and I will explain about one or two of them, that how I have written it. For the last one, you can see the last one. We have to see where the 1 or high lies in the output, and for the last output where there is 1, you can see the A is 1, which means A comes as it is. B is 0, which means we have to write B complement. C is 1 and D is also 1, which means that we have to write C and D as it is as well. Same goes with the one before the last one, this one. A is again 1, B is complement, C is 1 and D is complement. So their product will be A, B complement, C, D complement. And all these products are then added into each other. That is why it is called as a sum of products form. Now for the implementation of this form, I will show you the circuit which I have made to verify this truth table as well. This is the circuit, and this first input is A, B, C and D. These 4 are their nodes, and these are the resistors to remove the gray voltages, and this LED will indicate whether we have a high or low logic at the output. So if I run this simulation, for the first input to be high, we can see this D or C have to be 1. So if I make D1, there is 1 at the output. At C there is a 1 at the output, but if both of them are on, there's nothing at the output as indicated in this truth table. Now for B to give the input, B has to be on with either C or D. So if I turn the B on, it does not work with both C and D on as indicated from the truth table right here. B and C and D are all 3 on, and there is nothing at the output. So to turn the LED with B on, C or D has to be turned on with it. So if B is on and either C or D is on, we can see that LED glows. For the LED to give output at A, either A itself has to be on, or it can be on with C, D or both of them. So if I turn the A on, turn the B off, C, D and both of them, LED still gives the output. Now if A is turned on with B, as you can see from here, there's nothing at the output no matter what the value of C or D is. So if A is on and B is on, no matter what C and D are, the LED will not glow. So this behavior has been studied with this standard SOP form of the circuit. Now one drawback of this standard form is the circuit is quite big. As you can see, it involves 8 AND gates that have 4 inputs, then 3 OR gates to give out the sum of these ANDs. So this circuit is quite large, and that is why it is not preferred in practical applications. So what we do next is we convert the circuit or the equation into simplified form by the use of Kmaps or Carnot map. This is the Carnot map of the truth table shown before. Now the columns in this Kmap represent AB and the rows represent CD. The first two columns are denoted by A complement, the last two columns are A's, and the center two columns are B's, and the columns at the far left and far right are B complements. Same goes with C and D here. The center two rows are D, and the topmost and the bottommost are D complement. First two rows are C complement and the last two rows are C's. Now using the standard SOP equations, ones are put in their respective positions. Now if I explain about one or two outputs to you, A complement, B complement, C complement, D. Now this is represented as A complement, C complement, B complement, and D. So this one here represents the first product, and that goes on for all the other products. So there is a total of 8 ones in the Kmaps. Now the next step is to group these ones in a number of 1, 2, or 4, which means that they have to be in the power of 2. So the first group becomes this one, the second this one, and the third this one. After the grouping, we can see that there is a total of 3 groups. So there will be 3 products, and we have their sum, which will basically give out the same output as this equation. So what we have to do is, in this first group, you can see we have to point out what are the things that are common. So in this first group, A complement, C complement, and D is common, so it is written right here. And in the next group, A complement, C, and D complement are common, so it is written right here. And in this last group, A and B complement is the common, and it is represented right here. Now this is the circuit that is obtained from the Kmap and the equation that we obtained from the Kmap. This was the truth table, and this was the Kmap and the equation that we obtained. Now this equation is confined to 3 products, and the circuit becomes a much simpler one, which increases the practicality of a particular function. Now the function works the same. At D it is on, at C it is on, at both C and D it is off, at B with C and B with D it is on, but B with C and D both turns off. A alone is on, but A with B is off no matter what C and D are, and A with C and D is on, which verifies the truth table that was shown before. Now the same circuit will be implemented on Verilog using a simple code in which we will put the same equations in the Verilog HDL code, and we will verify the truth table using the waveforms obtained. Now the same equations are implemented in the Verilog HDL. This is the name of our module. These A, B, C, D, standard out, and Kmap out are our parameters. A, B, C, and D are assigned as input, and standard out and Kmap out are the outputs. Now the standard out or the standard output is the output that will be obtained using the original or the standard form of the equation, which I have written right here. This sign represents the NOT, and this sign represents the AND. This represents the OR, and you can see this equation, even writing it in the Verilog HDL, it's a bit of a task, as the equation is quite long as compared to this Kmap simplified equation. You can see it is confined to 3 products. Now after this code is written, we are left with this RTL view, and this is the waveform that is obtained from these equations. The first thing you must notice is that the standard output and the Kmap output have exactly the same waveforms for the same inputs, which means that the standard output, the long equation, gives the same results as the simplified Kmap equation. Now, to explain how this is actually working, the A is the most significant bit, so it is given the highest value of period, and B, C, and D followed, each having the half of the previous one. So to verify the truth table, you can see that a high is obtained for the first part only when C or D are high. When both of them are high, you can see that there is a low at the output. Now to get a high at B, it has to be high with either C or D, as it cannot have a high value with both C and D high. After that, to get the output 1 or high at A, either A alone has to be high, or A has to be high with C or D or both of them. Now after that, if the A is high with B, you can see that there is a low at the output, which basically confirms that the truth table is verified with the equation, and the Kmap equation is a simpler, more effective and practical procedure to work with these truth tables and equations. So I hope I have helped you learn a thing or two. Thank you very much. Allah Hafiz.